because one of the students did that, and that was good. Okay, so let's see what we're going to do today. We're going to go more in frequency domain, deeper. We're going to talk about power spectral density characteristic of that. And we want to make you ready for filtering. Filtering is like transformation in random variables, but for signals. Right now we are in signal part, because signals are actually random process is a kind of signal, and if you want to transform it, you need to do filter. You need to use filter. And we want to see if exists any filter that we can use that filter to whiten a correlated signal. If you have a signal that is correlated, so it's not flat, it's, for example, most of the energy is in the low frequencies, for example. Can we make it flat? Because if we make it flat, later we can use, for example, Markov model that we saw last week. How amazing they can to do learning, for example, using AI, using tracking. Markov models are very well actually design model, and you can get very actually good solutions. The answers are very precise. Is not you are not approximating. You get correct final answer from it, and that's because of characteristic of Markov model. The point is, you can find the next step just with multiplying a transition matrix with the previous state. That's amazing. And with whitening, you can do that. If you have a model that is correlated, you can white it. You can whiten it. How we can do that? Using these techniques that we're going to learn, not today, next class mostly, but I'm going to make you ready for that. That's the ultimate or the last part of this frequency domain that we started. We want to see, can we find a filter that whiten random process? Yes, we can. And we want to see how. In a frequency domain is easier to work on that. In frequency domain is easier. We can see why. Okay, so that's the topic for today. And we can see that with a spectral factorization, we can do this whitening. We can start it this week, today, and finish it probably Wednesday. Just recap about power spectral density. We know the power spectral density showing how power of a signal distributed in different frequencies. Like, for example, most of them are in a lower frequency, most of them in higher frequency, or all flat distributed evenly around all frequencies, like white noise. And to find frequency, we need to, okay, so before we get one step back, okay. Let I tell you something. So we know if we want frequency, if we want to see how a signal, for example, this is a signal. We want to see how the frequency changing in this signal. This is the power of signal, for example. This is time. So what we need to do, we need to study how, for example, this is xt. We need to study how xt compared to xt plus tau changing together, like how they are differing from each other. This is showing us how this actually, if you want to study the frequency of this signal, we need to work in these two cases. We want to see how this signal changing, if we shift it, like a little bit shifted, how they are changing. So that's why we need to study about expected value of xt and xt plus tau. And we call that autocorrelation. Okay, so autocorrelation and frequency part of the signals are very actually close. That's why if we change this autocorrelation to frequency domain, how? Fourier transform. If we get Fourier transform of autocorrelation, this is going to give us those power spectral densities. So this is the relationship between autocorrelation and power spectral density. Power spectral density showing how power of this signal distributed around different frequencies. For example, if this is frequency and this is power spectral density, is like this, for example. So it means concentrated in the lower frequencies. This is like a low-pass filter. Low-pass signal. Okay, so so this relationship, these connections coming from that. We already talked about this. We also in discrete space, if we, instead of having time, imagine we have time slice or k. If we have time slice or k, we, instead of having omega, that is angular frequency, we can have z or z. That is z is e power jw. The j is actually imaginary number. We're not going to go deep in that. If you start talking about frequency, you need to go so much deep in the like imaginary space, you know, unit circle. But we don't want to go touch them because that's going to be not related that much. We want to just concentrate in a main part, that the main part is whitening. The end of this class, the things that I want to take out from this part is just whitening part. How you can do whitening. Because whitening, I told you how important is that. And how much application. Because with whitening, you can make the model that is correlated and is not Markov. Markov. You can change it to Markov. And Markov model, you know how amazing is that. You see application of that. And for your next assignment, I ask you to design something, whatever question that you coming to your mind, you just use Markov decision model and model it with that. That's actually good part. And I hope you find something amazing and find that useful as well. Okay, that's frequency in discrete time equation, or a Fourier transform in discrete time. So what this showing, this power spectral density showing, for example, for frequencies Z or Z, the output is just a number. Showing for each frequency what is this power, showing that power in that frequency, or average power. It's just the average power because we are adding them together. It's kind of averaging. For frequency omega, or in discrete time Z. Okay, then a unit of that is a radian per sample, or radian per time, per second, if it's continuous or if it's discrete. Okay, so that was something that we explained last class. Today we're going to talk about more characteristic or more properties of power spectral density. The first one that we already talked is a Wiener-Khinchin theory that's showing how power spectral and autocorrelation are joined. They are joined. It means if you get Fourier transform of autocorrelation, you're going to get power spectral, and vice versa. If you do inverse Fourier transform of spectral, you're going to get autocorrelation. And I explain why. Because autocorrelation showing how a signal change compared to a little time later of that signal. So autocorrelation is like that, and that's showing how in frequency, it means getting Fourier transform of that, getting power spectral density. So imagine this is the signal, and this is a little later of that signal. If you compare these two, you can see how this is changing in time. If you see how it's changing in time, you can see how it's changing in frequencies with after getting Fourier transform. That's why autocorrelation and power spectral density are pair, Fourier transform pair. Okay, that's the main thing that we need to know. That's the Wiener-Khinchin theorem. The other characteristic that is actually coming from also autocorrelation part is real and even. Because if you remember last, maybe a couple of classes later, when we draw autocorrelation was always even. It was like this all the time. Or for example, like this, for example. If it's 0 here, it's even. It's always even. Autocorrelation is always even, so that's why PSC is always even and real, because autocorrelation is real. And when it's saying is even, means power spectral density of omega is equal to power spectral density of minus omega. It's not negative because it's power. Power is not negative. Power is always positive, and is always bigger than 0. Okay, later we can see in factorization how we can use this power, this idea that is power. You can say, okay, can we factorize it if it's power? Can we find that power? So that's why that's so important. That's why this power spectral density and studying that is very important in terms of whitening. Whitening is the last part that we're gonna learn from all of these things that we are talking. And then power in frequency band. Even we can study not just one frequency. What about the frequency band? We want to see what is the overall power of the signal in this band between, for example, this frequency to this frequency. So easily you just can get integral. If you want to see what is the power of the signal between these two frequencies, you just need to get integral of power spectral density in that band. That's it, easy. But the last one is the most important one. More important one. And that's about filtering. So I explained what is filtering. Filtering is how we transfer signals. Let's clean this up. In random variables, we said, okay, we have x, and if you want to transfer it, we can transfer it by a function g and say, okay, the new one, y is g of x. That's what was transformation. In vector, random vectors, we said, okay, in random vectors, you also can transfer. We need to find a transition matrix, for example. And this transition matrix, for example, is H. And you just need to dot product that with a matrix X to get Y, for example. Or maybe this is transpose. So we also talk about that. But in signal or random process, transformation happening with filtering. And transformation is actually convolution. So you just need to convolve. If you want to transfer a signal like this by in frequency domain, if you want to, in time domain, with h of t, that is h of t is a function. You just need to, actually, this is x of t, and this is h of t. You just need to find convolution of h of t and x of t. It's going to give you y of t. And that convolution is a little, because it's an integral and you have, it's complicated too. But studying the frequency of that is easier. Why? Because if the power spectral density of x is s of x, omega, power spectral density of y is just the S square magnitude coming from S square magnitude of that filter. We call that filter H by Sx of omega. So it's showing them in actually frequency domain. The new power spectral density is just same as previous power spectral density, just multiplied by a square magnitude of the filter. This is called frequency response. Response of H. Okay, we can study this. So what this, and this is give us the idea, if we can find one of these H that make this part constant, if we make this part constant, like it's 1, so this means we already whitened that. If you find one H that after multiplying with S of x get a constant number, so we need to find this frequency response, this H, that when we multiply the power of a square power of that with S, get a constant number. So this means whitening. That's what we want to get at the end of this class. Okay. That's why this part, relationship with filtering, is an important part. Okay, let's see how we can explain that. Okay, let's have some example first. First example that is always coming first is white noise. So white noise is white, so it means the autocorrelation is 0. But autocorrelation is everywhere 0, but not in a 0. In a 0, 1 is sigma 2. The sigma 2 is the power of that, but in other places all 0. So this is coming from this delta function. However, it's in discrete form. So in this delta, when k is equal to 0, delta k is 1, and if k is not 0, that's 0. So it's showing autocorrelation is everywhere 0, but not when the k is 0, and not in a starting time. When the starting time is 1. So in this case, if we do power spectral density is kind of flat. It's not concentrated somewhere more, somewhere less. They are kind of flat. This is a white noise. So white noise is a type of noise that we always want to make because there is no correlation between in time. So we want to have this. We want to have white noise. If, for example, have a system that the noise is not white, we need to make it white to kind of study it better, to make it Markov. Because in Markov, if you remember, we said we can define the state, next state, like xk plus 1, is a matrix F, for example, by x, plus some input, we don't care about that, but plus a white noise. This white noise, if this is correlated, if this noise, if this W is correlated, we can write this. Later, in end of this class or next class, we're gonna say if the W is correlated, after whitening, we can write this, but instead of having this X, we need to augment that with something else for whitening part. XKW plus 1. This is going to change too. This is going to change too for the whitening. We're going to see that later. So that's the last of these 2 sessions that we're going to have. So that was for white noise. So the white noise is something that we want to get from the correlated noise or any correlated actually signal or random processes. One of the correlated one is actually low pass signals or AR, autoregression, degree 1. Don't know what degree 1 is coming, but this is called autoregression signal. This autoregression degree 1. So in this autoregression, the autocorrelation is a function of sigma, of course. Sigma is showing the power. There is a variable a, that is a is less than 1. Because it's less than 1, we want to make the decay property. We want to, it's like a discount factor. I talked last class about this. When the k increasing, this power decreasing. That's why after changing to frequency domain, after actually finding power spectral density, these powers are more concentrated in a lower frequencies, as you can see. this is actually colored noise. This called colored noise. We need to whiten this kind of noise later. We can see if we can find a filter that can whiten that. That filter is a whitening filter. Okay, so if we draw autocorrelation for this, autocorrelation for this is gonna be something like that. Because autocorrelation is even. Autocorrelation for this is gonna be like that. This is our tau of x, and this is time. Okay, what about sinusoid signal? Sinusoid signal is the type of signal that is actually sum of sine and cosine. Like for example, like x of k in a discrete space is, for example, a cos of, for example, k plus b, for example, or there is another variable here, for example, something like that. So in this case, it's just if there is a cosine or sine, the autocorrelation is periodic. If we draw, for example, autocorrelation gonna be something like that. But it still is even. This is 0. This is r of tau, k, and this is t. This is periodic. Periodic means it's repeating. The shape is, but the shape in PSD, because it's just showing one frequency, all the concentration is one frequency, is going to be like a spike. Yeah, I draw it a good place, so it's not going to interfere with that. As you can see, it's just a spike. Based off the frequency of that, based off these numbers that we mentioned here, it's going to make just one frequency. It's going to be just one spike. So that's different between, this was just example of different type of signals and PSD of them. So the white signal, white noise, that PSD gonna be evenly distributed for all frequencies, like white noise, white color, for example, or white light. And for autoregression, that is, for example, low pass, most of the energy is in low frequencies. And for sinusoid or that is just a spike. All of the energy is just in one frequency. Okay, so let's go for filtering now. Now we have enough information or the backbone to understand how we can do with whitening. So we realize, okay, so if we do, if we want to do whitening, we need to find a filter to do that. If we want to find that filter, the simplest way is to work with PS, power spectral density, because relationship exists between filtering and power spectral density, and that relationship is here that we're going to explain it again. So filters in signals. Filters act as an operator or transformer for signal, like what we did before in transforming a random variable or transforming a matrix, the random vector. We also have here, if you want to transform a random process, we need to find a filter to do that, find the proper filter. So the filter doing actually can do emphasize certain frequency component, or also can remove some unwanted part. All of those parts can happen with filtering. So the filtering is important. So mathematically, filtering doing actually convolution. So the convolution is the main operation, like mathematically happening when you want to do filtering. So for example, if h of t is an impulse response of a filter, so to do filtering, you need to have impulse. Impulse is just the direct delta function. Impulse response of the filter. So h of t is that, h of tau is that, t is that, but when we go to the convolution, as you can see, convolution is so familiar, no? It's very similar to autocorrelation, but it's not between one signal, it's between two signals. So convolution is kind of actually showing how one signal changing compared to transform, because this is transform of another signal. How these two changing together, related together. And like mathematically, anytime you want to see how one signal blade the other signal, or maybe destroy the other signal or change the other signal, we can do convolution. And the reason is like that. As you can see how these frequencies compared to the other, how this signal compared to the other signals that changing in time, they are evolving together, they are changing together, they are blending. So that's the reason of convolution, and that's why filtering is kind of transforming a signal to another signal. That, as you can see, this can emphasize some certain frequencies more or less, or it can remove some unwanted part. So that's what we want. We want to remove the part that makes uncorrelated part of the signal. We want to a correlated part of the signal. We want to make it white. We want to make it white so we can use filtering. Okay, so let's see how we can do that. Clear this. So yes, that's the impulse response. So in frequency domain, that was in time domain. In time domain is convolution, but in frequency domain it's just multiplication. It's very simple. So if you want to actually filter x, you just need to multiply that by impulse with actually frequency response. That's called frequency response in frequency domain. So you just need to multiply that in frequency domain. In actually time domain, you need to convolve that or use convolution. Okay, that's it. This h of s is also called a scaling transformation because it can change it in a frequency domain. Okay, now we have all of the steps to see how pre-whitening works. Why we call it pre-whitening? Why we not just call it whitening? Because in most of operation, we first doing this part. That's called pre-whitening. To start other part, we just do pre-whitening first. So the pre-whitening is just finding the filter, proper filter to do that, because I mentioned that filter is the main part. Whatever change you want to do in a signal, you need to find proper filter. And this filter is kind of transforming a colored random process to a white process. Okay, so how we do that, let's see how we can do that. So we talk about this convolution part, we talk about this one. Okay, this is the main part. Okay, so as one of characteristic of power spectral density, we said, okay, if we transfer one random process by a filter called h of f, the power spectral density of that changing based of a square of magnitude of that filter, based of that formula. So we want to change it somehow, that power spectral density becomes constant. So what about we just put that constant and find h of f? That's it. That means actually whitening. So finding h of f is our purpose. So that's what we need to do. We need to find h of f. But it's not as easy as I mentioned, because it's kind of, if you want to find this, the easiest constant is 1. You just can put that 1 and say, okay, h of f magnitude square is 1 over sx of f, okay? And then, so h of f is going to be 1 over the square root of sxf. Okay, so that's a little complicated to compute. But what about, because we know that this is the power, so this is already a square. We know that this x is a square of something already. We know that. If we can factorize s of x, factorize means what? Factorize means find this value that is actually power of something. We need to find that part. That's called factorization. So this is relationship between pre-whitening and power spectral density factorization. Okay? Any question? Okay, so let's see how we can do factorization. The logic behind whitening, I think this is exactly what I already explained. So the white process has equal power, so that's, I think I already explained that. So we find this constant, the easiest one is 1, so that's, I already explained. And this is the ideal pre-whitening filter in frequency domain. So, okay, let's see how we can factorize spectral density. So this, we're going to talk about that mostly next class, but I just gonna just explain this slide, but not gonna go deeper. We can explain that next class. We also I wrote a code for that to show in Python, the same in MATLAB also, of course, how we can use this filtering. So we need to find this factor, h of f. So factorization, power spectral density factorization, it means to see how we can find this h of f. It exists because we already know that power spectral density is powered by 2. We already know that. And so we need to find this h of f and also h star of f. That's called a conjugate of that. So complex conjugate and h of f. We need to find these two, however, just h of f is enough. So this is what we're going to do. And that's coming, it's the new topic next class that's called shaping filter, how we can find shaping filter. So we're going to talk about that more next class. Oh, I have example here, I forgot. I have the example here. I was thinking I put that for the next class, but I have example. Okay, in this example, I created a signal that is actually autoregression. This signal, it's AR, autoregression. Autoregression is like a low-pass filter. How I made that, I used actually this filter, h of s, h of z is equal to 1 over 1 plus 0.9. We're going to explain that next class as well, but here we're just going to see how it works in programming. So I made one filter. I made some random white noise. This is white noise. I transferred this white noise with this filter to color that. So I colored that. It is the filter that I use for coloring that. The output is this, the blue one. And then I use another filter, that this filter is actually, if you multiply this one, this h of w of z is 1 minus 0.9 z minus 1. If multiply this with this, you're going to get 1. And then again, filter that. This L filter is a function that exists in Python, linear filter. You're just going to give A and B, and A and B is just this A and B. And the X is the input. So, and then I transfer that by this new matrix, this new filter, and draw that again. And this green one is after filtering. And as you can see, it's become flat. So this was a simple example that showing how in programming languages like Python or MATLAB, MATLAB is the same too, how we can use these methods. As you can see, we used, we just generated this correlated or colored signal. That's a color signal, AR, autoregression signal that is concentrated in a low frequencies more. The energy is concentrated in lower frequencies. And then but in reality, we don't know that. We don't know how this generated. In this example, we knew that the filter that made this colored was that. That's why we find the negate of that easily. But in reality, it's harder. That's why in reality, we need to go for power spectral density to find it. Okay, any question? Okay, next class also we are talking about a frequency domain. But after that, we're going to go for something very amazing new. A new thing is called actually Gaussian process. Gaussian process is amazing. It's lots of application, and we can see application of that soon.